Welcome to The Explainer. Today we're going to dig into something you probably never think about. It's the invisible math that, literally stops our world from falling apart. We're talking about the science that keeps those massive skyscrapers standing and our deepest tunnels from caving in. It all comes down to a set of brilliant equations that hold up our most ambitious creations.
So let's just think about this for a second. How do you actually build a skyscraper on something that can literally turn to mud? I mean, that's the core engineering challenge for any massive project, right? The ground beneath our feet, it can shift, it can sink. It's not just a simple solid block. It's a super complex, kind of unpredictable material. And if you misjudge how it's going to behave, well, that can lead to absolute disaster.
Okay, so here's how we're going to break this down. First, we'll look at the ground's deceptive, tricky nature. Then, we'll get into why the old models just didn't cut it. After that, the big breakthrough in soil science. We'll see how they proved it actually works, and finally, how this thing became the model that builds worlds. Let's jump in.
All right, Section 1, the ground's deceptive nature. So first things first, we got to talk about the ground itself. To an engineer, soil isn't just, dirt. It's a material with a really tricky personality. Figuring out how it's going to behave under the insane weight of a building, well, it's not straightforward at all. It's absolutely full of surprises.
So, picture this. You squeeze a wet sponge. It gets stiffer, right? Soil's kind of like that. But, and this is the huge difference, when you let go of the sponge, it bounces back. Soil? Nope, it doesn't. It's been permanently changed. It actually remembers that first squeeze. And that memory, that's the exact thing these early engineering models just couldn't handle. A massive and, frankly, dangerous blind spot.
Okay, Section 2, old models, critical flaws. This brings us to how things used to be done. For a long time, engineers were relying on these formulas, a type called a hypoelastic model. The problem was it had this really fundamental, kind of dangerous flaw, an inconsistency that really pushed scientists to find a much better way.
So here's the deal. The most popular old model, it had this huge blind spot. It literally could not tell the difference between the first time you squash the soil and any other time you do it. In the math, they looked identical. But think about the real world, where the ground is constantly being loaded and unloaded by traffic, by wind, by whatever. That's a fatal flaw. It meant you could never, ever truly trust its calculations for when a structure might actually collapse. And that is the exact problem the hardening soil model was designed to solve.
Right, on to Section 3, a breakthrough in soil. So what was this big aha moment? Well, the hardening soil model wasn't just some tiny tweak. No way. It brought in some absolutely brilliant ideas from a field called plasticity theory. That's basically the science of how stuff, like metal, or in this case, soil, permanently bends and changes shape when you put it under stress.
And this is where the genius of the model really comes into play. It has three key innovations, like three tricks up its sleeve. First up is double stiffness. It uses one number for that brand new first-time squeeze, and then a totally different, much higher number for all the unloading and reloading that happens after. Super smart. Second, isotropic hardening. The model gets that as you compact soil, it gets stronger. It builds that right in. And finally, the yield cap. This is a really clever feature that models what happens when soil gets squeezed from all sides at once, like deep underground.
Okay, let's zoom in on that idea of hardening for a second. Isotropic hardening. It sounds complicated, but it's based on a really simple physical truth. As you compress soil, it gets stronger and stiffer. The snowball analogy here is just perfect. The more you pack a snowball, the harder and denser it gets. The model takes that exact same logic and bakes it right into the math.
So what does this mean in practice? Well, the practical result of this hardening is that the model's safety boundary, you can think of it as its safety limit, it isn't a fixed line. As the soil gets stronger from being compressed, that boundary actually expands. It grows. This captures how the ground can essentially learn to take on more and more stress, which is a really dynamic behavior the old models just completely ignored.
Okay, Section 4, from theory to reality. So, look, a clever idea is one thing, right? But it's just a theory until you can prove it. So the creators of this model, they had to put it to the ultimate test.
They basically set up a showdown, the model's predictions versus hard data from real-world lab experiments. It was time to see if the math actually held up.
And they went about it in a really classic scientific way, a three-step process. Step 1, calibrate. They basically taught the model the basic properties of a specific material, this stuff called loose host and sand, using standard test data. Then, step 2, predict. They took that trained model and used it to predict how the same sand would behave in new, much more complicated experiments. And finally, step 3, compare. The moment of truth. Did the model's predictions actually line up with what happened in reality?
And that first step, it was a huge success. The original paper from the researchers said there was a satisfying comparison between the experimental and a numerical result. What that really means is the model nailed it. It had learned the behavior of that horsekin sand almost perfectly. But then came the real test, the moment of truth. Could it actually predict the outcome of completely new, more complex scenarios? Things like undrained shear tests. And the results? They were pretty incredible. The paper itself called it a very good agreement with the measured data. The model wasn't just repeating what it had been taught. It was genuinely predicting behavior it had never seen before.
All right, section 5, the model that builds worlds. And this is probably the most important point of all. This was never just some abstract academic exercise. No, this model had a profound and immediate impact on real-world engineering projects all over the world.
And its power, its real power, was in how practical it was. The inputs the model needed, things like friction angle, cohesion, these were already the bread and butter for geotechnical engineers. They were things they worked with every single day. So it didn't force them to learn some whole new scientific language. It just gave them a familiar-looking dashboard to control a much, much more powerful engine. And because it worked so well, it was adopted almost instantly. We're talking 1999 here. That's the year the hardening soil model was formally introduced, and boom, it was implemented right into Plaxis, which is a huge software package that geotechnical engineers use for everything. This put an incredibly powerful new tool directly into the hands of the people actually building our world.
You know, that was really the goal all along. The creators themselves said it best in their paper. They wrote that the model is very attractive for the use in daily geotechnical practice. They knew they had built a bridge, a successful one, from really abstract, high-level theory to the muddy, messy, practical reality of a construction site. And it really makes you think, doesn't it? This is just one elegant piece of math for just one material, soil. So what other invisible mathematics, what other brilliant models like this one are silently at work all around us, holding up the very fabric of this complex world we've built?